Hi everybody. So we're going to start with a short example that takes what we did in class today and makes it a little more practical and applied. So here's the problem. We have a guitar string, and that string is stretched between two supports that are 0.640 or 6 meters or 64 centimeters apart, and this length of string also has a mass of 2.86 grams. When the string is plucked, it plays an A, which has a frequency of 110 hertz, right here, in its first harmonic mode. So it's vibrating in the first harmonic mode, and that makes it play an A at a frequency of 110 hertz. What is the tension in the string? Okay, so let's figure this out. First thing you have to do with these kinds of problems before you do anything else is sketch it. So we know we have a guitar string fixed at both ends. We know it's vibrating in its first harmonic or fundamental mode, which means it looks like that. We know the length of the string is 0.640 meters, so that's the length of the string. And we know it plays on a frequency of the first harmonic of 110 hertz. So when I pluck that guitar string, it vibrates up and down in that fundamental mode at a frequency of 110 hertz. That's great. Okay, we want to figure out the tension. Well, I know to figure out the tension, I need to know the velocity, because I have for my strings an equation that the velocity is the square root of the tension over the linear density, which, if you recall, is the mass per unit length. I do have the mass, and I do have the length, so I can get the linear density. So I'm going to go ahead and do that right now. But we see quickly that in order to get the tension, we need to get the velocity. So this problem really amounts to getting the velocity. But let's do a little side calculation here to get the linear density. Remember, the linear density is kilograms per meter. So 2.86 grams, I have to divide by 1,000, so that's 0.00286 kilograms divided by 0.640 meters, and I get that my linear density is 286 divided by 0.640, and I get 0.00447 kilograms per meter. I'm going to need that later, so I'm just going to save it. Okay, now I'm going to come over here, and I'm going to say, how do I get the velocity so that I can use the linear density to get the tension? And in order to get the velocity, I need to use my wave equation. My wave equation is V equals F lambda. Well, I do know my frequency is 110 hertz, but I need to get my lambda. Now, I know the length of the string is 0.64 meters, and here's where, and this is the most important step when you're working with standing waves, you have to figure out how to use the length of the object and figure out the wavelength of the vibration. If you recall, for the fundamental mode, the length of the string, L, in this case, supports a half of a wavelength. What that means then is the wavelength of this vibration is twice the length of the string, which is 2 times 0.640, and 0.640 times 2 is 1.28. So that's my wavelength. Now I can come over here and I can use my wave equation. V equals the frequency, 110 hertz, times the wavelength, which is 1.28 meters. And I wind up with 140.8 meters per second. That's great. So now all I need to do is take my velocity, take my equation for the speed of waves on a string, use the linear density that I calculated and get everything that I need. So I'm going to move this up a little bit. Ooh, that was very stretchy. I'm going to move this up a tiny bit. All right, let's do the last part. So the last part is going to be me using my equation, velocity, which is 140.8 meters per second, equals the square root of the tension, which is what I want, divided by the linear density, which is 0.00447 kilograms per meter. I square both sides, and then I get, let me move that up again. I square both sides, and I get 140.8 squared times, then I cross multiply 0.00447, and I wind up with a tension of 88.6 newtons. And that's how tight I need to make the string in order to make it play that note.